Okay, guys, so I'm pre-recording this one just so that you guys are able to review it before starting the practice exam. So the practice problems will be posted by 7 p.m. tonight. I'm just finishing up, making sure that everything works out the way I want to. One little note to disclose is when I took this course, a lot of the practice problems that I put on the practice exam are based on old questions that I got. We took it on paper, so we got back our exams. So a lot of them are based on ones I've taken, and through the years I've adapted them more and more. But at Electrochem, in many years prior, we've had only it on the final, so we actually haven't been able to get back and see how they ask these questions. And so these are kind of just my best guess as to what they would ask. But I would definitely go and put in some good review work on Electrochem, Chapter 18. And a lot of the problems, there are similar ones in like Dr. Katie's slides, adaptations of those. A lot of it, electrochem's not necessarily the worst subject for a lot of people. It's mostly just applying the vocab. Um, they can give you a lot of information in very few words in electrochem and kind of expect you to make that jump. So definitely watch out for like problems like that. But to start out, we're going to go through just two electrochem problems, right? So we're going to go through one is just finding the cell potential, but there's a little twist on it, and it's something that you guys should definitely 100% know. Because if you're not familiar with how to do it, you might just make something that's a very common error in electrochemistry. And then electrochem problem two is going to just be using those like conversion units, so like ampere and coulombs. It's going to be a problem like that. If you want to review more problems, I know at least Dr. Katie has three or four good examples, so maybe look over those. But I don't think that'll be a huge focus on your exam. Just be familiar with the units and how you'd be able to interconvert between them. And then we'll go through the major points in thermochemistry and electrochemistry. And again, the hope of this is that you guys can watch this and review it before doing the practice exam. And then any remaining questions from the practice exam or kind of this quick review, you can bring to the session on Wednesday, which will be back to the normal time at 7 p.m. Okay, so the first problem again is a very classic question. What is the cell potential of a spontaneous cell containing the following half reactions? Right, so here I tell you it's a spontaneous cell. So a spontaneous electrochemical cell will have a positive cell potential. So when we add these these potentials, these E values, it has to come out positive. Now they're both in terms of reduction here, so we know we have to flip one of them. Okay, so in this example, I use the word spontaneous to tell you that our E, when we add them together, has to be positive. But I could have also written, what is the cell potential of a galvanic cell containing the following half reactions, or a cell potential of a voltaic cell containing the following half reactions? All three of those terms are synonymous in meaning that our E value has to be positive. Okay, and when we add reactions together, it's redox. We always need one to be oxidation, one to be reduction. So we're going to flip one, which means their sign's going to change. And if we need it to become positive, that's how I know that that K equation, that potassium equation, needs to be flipped. Okay, so again, it's spontaneous. I need a positive E. And if you ignore that 3 for a second, I just flipped the potassium equation. So instead of it being K plus on the reactant side, it is now solid potassium, goes to a potassium ion plus an electron. And you'll notice I wrote E oxidation, right? It's in terms of oxidation now, not reduction. And all I did was change the sign. So it's positive 2.936. It's no longer negative. Now you'll notice I multiplied it by 3 as well. And again, you might remember last semester in Chem 1127 that when we added our two half reactions, which is what the previous slide really was showing, we need equal number of electrons transferred, right? So our chromium equation involves the transfer of 3 electrons, which means for these to be fully balanced, we actually have to multiply this equation by 3 as well. And so I multiply it all by 3. So now it's 3 potassium solid molecules go to 3 potassium ions plus 3 electrons. And so when we add those together, you'll notice the balanced equation at the bottom has no electrons because they cancel out. A really, really important point to make here is that you'll notice our E oxidation, even when I multiplied it by 3, does not change. And that is a huge component of electrochem. When you multiply an equation by a coefficient, it actually does not change your E value. Okay, that's a very, very common mistake. So definitely note that. So you'll notice it just remained at positive 2.9 or so. Our reduction, which is that chromium equation, is equal to negative 0.744. And so to get my cell potential, I just add those together, right? So it's 2.936 plus negative 0.744. And so my standard cell potential would be 2.192 volts. Okay, so again, the big point I wanted to make here is that if you have to multiply by a coefficient, you don't actually multiply the E value by that number. Another point I want to make, and like the reason you might say, okay, if we don't multiply E by 3, why do we even multiply it at all? Like, I might know that it has to be multiplied by 3 to be balanced, but why do we care? And when we're converting between our cell potential, E, and delta G or K, right, our equilibrium constant or our change in Gibbs free energy, we have a term called N here, right? And N represents the number of moles of electrons transferred in the balanced chemical equation, okay? And so when you have two equations that transfer different number of electrons, you have to make them the same number, and that's your N value, right? So we have one equation that initially transferred 1 moles of electrons, another one that transferred 3. So N, which represents the number of moles of electrons we transfer in the balanced equation, would have to be when those number of electrons are equal, which here is 3. Okay? And so to know what that true N value is, you have to make sure that you multiply the equations by the respective coefficients so that those electrons do cancel out. Okay, and then it's that coefficient when they cancel out that is your N value. That's a little bit confusing. I'm trying to keep it a little bit ambiguous still because I think there's a really good example of that on the practice exam. And so again, if that's a little bit confusing, bring it up Wednesday. We'll definitely go over it when we go over that problem. Again, I just don't want to give you 100% the answer to that so that you can kind of work on it and challenge your understanding of these topics. Okay. So problem 2, again, is one of those conversion unit problems. I'm not the biggest fan of these, so I'm sorry if the problem's not the best. But it's 100 grams of chromium undergoes reduction, as in the prior problem. That just means use the chromium equation from the last problem, right? So it's a transfer of 3 electrons, and it happens over a time span of 2 minutes and 15 seconds. What amount of amperes is associated with this reduction? Okay. So this is basically just one long stoichiometry problem, but I wrote some important information under it. Okay, so you'll notice amperes is actually coulombs per second, right? That's the units that amperes is equal to. And so we're going to want to convert to coulombs, and we're given time, right? 2 minutes and 15 seconds. You'll notice I converted that. That is 135 seconds, right? So we're going to divide it by 135 seconds once we convert to coulombs to get it in terms of ampere. Okay. And you'll notice I also wrote the equation, right? Chromium 3 plus is reduced to chromium solid. And the important thing here is that the coefficient of chromium is 1, right? So for 1 mole of chromium being reduced, we have a transfer of 3 electrons. That's going to be a crucial conversion factor in this equation. Okay, so if we have 100 grams of chromium is 52 grams per mole, right? So it's 1 over 52 is the conversion, and that would give us moles of chromium. Now we want to get to coulombs, convert to moles of electrons, right? So we just figured out from our equation that 1 mole of chromium is 3 moles of electrons. And then this next conversion factor is just like a known constant that 1 mole of electrons will always be 9.648 times 10 to the fourth coulombs. Okay, that'll be a value that you're given either on your equation sheet or on the exam itself. But that statement will always be true. So now if we look up at our dimensional analysis up to that point, right, we went from grams of chromium to moles of chromium, then we went to moles of electrons, and then we went to coulombs. So our units up to that point are coulombs, and so now all we do is multiply it by 1 over seconds, which is the same as just dividing it by seconds. And so when we do that math, it's coulombs per second. You do the math out, and it comes out to 4,123. And again, coulombs per second is equal to amperes, which is A, our unit for that. Okay. And again, if you want more, I don't think it will be a huge point that they focus on, but if you do want more practice, I know at least Dr. Katie has some a few more examples in his slides, and I'm sure the other professors do as well. Okay, jumping into the actual review portion. So thermochemistry, there's kind of 5 main points to hit on, right? There's Gibbs free energy, which is kind of broken down into components of enthalpy and entropy. Then we have non-standard Gibbs free energy, and then we have manipulations of delta G. Okay, so those are the 5 main components we're going to focus on for thermochemistry in this review. Okay, so I'm sure by now the equation for Gibbs free energy is nothing new to you. So it's the change in Gibbs free energy equals the change in enthalpy minus our temperature multiplied by our change in entropy, right? And what does it really mean? So if delta G is less than 0, aka it's negative in value, it is going to be spontaneous, which means it will just naturally go forward, right? It's favorable. That's a reaction that wants to happen. And the term we give that is exergonic, right? Exer kind of meaning out, meaning kind of like a release of energy, and gonic relating it back to delta G. If our delta G is equal to 0, that actually means that we are at equilibrium, okay? And that's definitely something that's important to know. And we'll see an application of that in just a couple of slides, okay? But if delta G is equal to 0, you are at equilibrium. And if delta G is greater than 0, aka delta G is positive, the term we use for that is endergonic, and that is not favorable, right? It won't go on its own. It needs an input of energy of some sort to help it go, okay? And one thing you're definitely expected to know, and we'll probably see in more than one problem on your exam, is a problem having to do with this chart, right? So given information about delta H and delta S, is an reaction always favorable, right? It's always spontaneous. Is it never spontaneous? Or is it spontaneous depending on the temperature? Right? So I think on my practice, and again, on your exam, I'd expect them to ask 1 or 2 questions. Just, is it always spontaneous, never spontaneous at high temperatures or low temperatures? Or at which temperature will this be spontaneous or not spontaneous, right? So if you want some practice with that, we've done a couple of different practice problems in SI sessions already. And so definitely go back and see some of those. Your professors should have gone along it as well. But for your exam, I would highly suggest either having this table in front of you or being able to derive it. If you can derive it yourself, you definitely have the understanding necessary to carry out these problems. And so from there, it's just understanding if you have to solve for the temperature in which it becomes spontaneous, kind of knowing that you have to set delta G equal to 0. And solve for temperature using delta H and delta S. If you know that, you should be set on one of those problems. And again, there's a couple for practice on my practice exam as well. Okay, enthalpy, which is delta H, we won't focus on too much because that was more of a topic of 1127 last semester. But it basically is a measure of bond energy dash the difference in bond energy. And the reason why I say difference in bond energy is we don't really look at it in terms of one specific time. We typically look at it as a change, right? We don't look at it as just H. It's typically delta H, which is, again, the difference in bond energy between products and reactants. Okay, and so some terminology from last semester, which hopefully you still remember. If delta H is negative, we term that exothermic. Exo, again, meaning exit or release, which means it releases heat. And positive delta H is an endothermic reaction, which means endo means in, which is absorbs heat, right? Heat has to come into the system. And just something to note is that it's typically measured in kilojoules, which actually becomes very important when we add in our new term, entropy. Okay, entropy, or delta S, is a measure of randomness disorder, right? And things like to have an increase in entropy. They like to become more disordered or random. Okay, so one thing to note is that entropy increases from solid to gas, right? So a liquid will have greater entropy than a solid. A gas will have greater entropy than both a liquid and a solid. Okay, and kind of the reason for this is that with increasing temperature, you also have increasing vibrations, right? So as you kind of increase temperature, you become closer to gas, right? And so it's kind of greater entropy. So if they ever have you compare something at two different temperatures, the higher temperature should have greater entropy or disorder because there's more molecular vibration, which is in essence molecular disorder. Okay, how do we calculate delta S? So we actually calculate delta S just like we do delta H and delta G. And it's the sum of the entropy of our products minus the sum of the entropy of our reactants, right? And they'll give you a table of values if they want you to solve for it this way. And just kind of remember that you have to multiply things by its coefficient, right? Because the units for it are joules per mole times Kelvin. And so to get rid of the mole portions, if the coefficient of CO2 is 4, I have to multiply the entropy value of CO2 by 4 as well. Other common mistakes when you're subtracting reactants from products, remember to distribute that negative sign, right? So write some big brackets around all of that. Make sure you add up all the reactants together and then subtract all of that from the products. And yeah, just one other thing to note, again, it's in joules per mole Kelvin. So just note that when you solve for delta S, it's probably still going to be in terms of joules, while delta H is in kilojoules. So just remember to convert one of those so that they're both in joules or both in kilojoules so that you can actually compare them and add or subtract. Just because you can't add or subtract them when they are different units, right? You can't really add kilojoules and joules together because they're off by a magnitude of 1,000. Also, some basic trends. So you should be able to, kind of what the last bullet point mentioned, calculate delta S based on a table. But something else you should be able to do is say which side has higher or lower entropy based on very basic trends, right? So if both your reactant and product side have just gas molecules on it, or mostly gas molecules on it, it's the side with more gas molecules that will have more disorder or higher entropy. And the reason is if you have 1 mole of gas or 2 moles of gas, the 2 moles of gas will collide into each other. They'll just be more spontaneous in a way. And so they'd have greater disorder. So being able to recognize that. And then the other one, and Dr. Katie, I know, has a couple really good examples in his slides of this. But if there's gas and solids in an equation, you kind of, the general gist that you see is that the solid is on one side, the gases are kind of on the other. And there might be other things. I think his example has aqueous on both sides too. But when you look at an equation, generally look at where's the solid, where's the gas. And typically they're on opposite sides. The side with the gas will have higher entropy. The side with the solid will be lower, okay? And again, if you want 1 or 2 examples to look at, his slides do have some excellent examples. But being able to identify that could be important for the exam. Okay, non-standard Gibbs free energy, right? So standard Gibbs free energy is when we have that little circle above it, right? So delta G naught is how we say it. And so this equation, the first one, kind of compares the two. So I would call non-standard Gibbs free energy delta G, with standard Gibbs free energy being delta G naught. And what you'll notice is that when we solve for non-standard Gibbs free energy, or just delta G, it's actually in terms of Q, which is our reaction quotient, right? So we kind of use this when we are not at equilibrium, right? If we are not at equilibrium, we are going to be solving for delta G, not delta G naught, okay? I know it's confusing because I said not after, but delta G we use when we are at any point in time. Delta G naught we solve for at equilibrium, right? And so one important thing to note, and we kind of talked about this a couple slides ago, is that when we're at equilibrium, delta G is actually equal to 0. And so when we work this equation, at equilibrium, we can only solve for delta G naught, and the equation for that is delta G naught equals negative RT times ln of K. And I would say, notice how in the top equation, we have Q, our reaction quotient. Well, in the bottom equation, when we're at equilibrium, we input K. And that makes sense. When we're at equilibrium, we should be using our equilibrium constant. When we're not at equilibrium, we should be using our reaction quotient. And then just kind of a quick note on standard states, which isn't typically too big of a concept. It's just, why do we have it? It's basically used as a basis of comparison for different reactions. So, for example, many of you are pre-med or bio majors and will take biochemistry. When you look at reactions that occur in metabolism, right? So reactions that occur in the body. For example, you might look at cellular respiration by steps like glycolysis. You can look at the delta G value or delta G naught values as like a unit of comparison, right? So you can compare different steps of glycolysis. And by making certain assumptions, it makes it kind of easier to see these comparisons. If you looked at them as just delta G, it would be a lot more complicated. Okay, so basically it's just used as a basis of comparison. And we have some assumptions. If something's in the aqueous state, we assume it's at 1 molar. If it's a gas, we assume it's at 1 atm as a pressure. Okay, and manipulations of delta G. So again, we've kind of talked about these for a while. The big thing is definitely don't get these mixed up with the electrochemistry manipulations, and especially don't get these mixed up with your equilibrium constant manipulations. Because again, each of these has its own unique set of rules. Okay, and so if you ever want to find the delta G of the reverse reaction, right, so you have to flip it, all you do is change the sign on delta G, right? So if A to B has a delta G of 2, B to A would have a delta G of negative 2. Okay? If you ever have to multiply your reaction by a coefficient, you just multiply delta G by the same coefficient. It's actually pretty easy for that. Okay? And then if we ever add reactions together, which is basically the exact same as what we used to do last semester, which was Hess's law when we added thermochem reactions together. If you ever add two reactions together, you just add their delta G's. Okay? Again, I think putting these in a chart could be really helpful for your final. But if not, definitely note the difference, at least for this exam, between manipulations of delta G and manipulations of E, because they do differ very slightly. But we will get to manipulations of E in a couple slides. Okay, so getting into electrochemistry review, we have a couple different things I want to touch on. First, we're going to touch on the components of electrochemical cells and the proper notation. We're also going to jump into terminology and types of cells, then our equations that we use, manipulations of E, and lastly, just quickly look at units of electrochemistry. Okay. So if you look at an electrochemical cell, you'll notice two really important kind of components, right? The first is pretty easy to see. It is an electric, like a wire, a metal wire, and that is how our electrons move. Now, it's really important that you note that electrons always move from anode to cathode, right? I could definitely see them asking something like that on the exam, right? Which of the following is true? And maybe they say electrons move from cathode to anode, which would be obviously false. So electrons will always move from our anode to our cathode. Okay, and that kind of makes sense when we break down what the anode is and what the cathode is, but we'll get there in a second. Now we also have a salt bridge, right? And what's the point of this? This is for ions to move between the two solutions, right? We have two different solutions that a solid metal is kind of dipped in. And the reason we have this is so that ions in the solution can go across that. And the whole point of that is to first complete the circuit, right? You might know from, I don't know, maybe 5th or 6th grade in science class, maybe you made a small little battery, or, you caused a light bulb to light up from connecting it to a battery. We all know that you need all circuits, which this is no different, to connect, right? So the circuit is kind of from anode, we would travel to the cathode via the wire, and then we can kind of travel back to the anode from the cathode with this salt bridge. Okay, so again, through the salt bridge, ions move, and the whole point is to balance the charge differential that is created by the movement of electrons, right? Because electrons will only ever move from anode to cathode. Okay, now we have our two electrodes, right? So it's breaking down anode and cathode. So anode is where our oxidation takes place. I remember that because they both start in a vowel, right? Anode, oxidation, A and O. And what is oxidation? Remember, that's becoming more positive in oxidation number, right? So you might go from oxidation number 0 to positive 2, right? You became more positive in oxidation number, and therefore it's oxidation. The cathode is where reduction occurs. And again, these both start in a consonant, which kind of helps me remember that. Okay? And what's reduction? Reduction is when you become more negative in oxidation number, right? So you might go from positive 2 to 0 in oxidation number. And again, I remember that by just saying reduction, reduced is becoming more negative, and so reduction becomes more negative in oxidation number. I know the chemistry professors like oil rig or Leo the lion says grr. Whatever helps you remember what oxidation is, what reduction is perfectly fine. We kind of went over that last semester. Kind of the jump this semester is that the anode is where the oxidation occurs, the cathode is where reduction occurs. In proper notation, I would expect to see this on maybe 1 or 2 questions. I had a problem, I think, last session where I gave you proper notation and had you solve for the E value based on the proper notation. So you had to know which side was the anode, which side was the cathode. But basically, the proper notation is that the first 2 things written is part of our anode, right? So our anode's on the left. Our anode is where oxidation occurs, and so our oxidation reaction is CD solid to Cd2+, which makes sense because, again, it's becoming more positive in oxidation number, which is oxidation. On the right-hand side, that is what is occurring at our cathode, which is a reduction reaction, which again makes sense. Our reactant for that would be magnesium 2+, and that is reduced to magnesium solid, right? So, and you'll notice there's a semicolon between these. So on the left side of the semicolon is our anode, which is our oxidation. On the right side of the semicolon is our cathode, which is our reduction. Okay, terminology and types of cells. I definitely think that this will appear multiple times on the exam, kind of hiding the information you need. And so just remember, and we kind of talked about this going through the first example, that the term spontaneous, voltaic, and galvanic all mean the same thing in electrochem, right? They all describe the same type of cell. And really what that tells you is that it has a positive E value, right? So if they tell you you have a galvanic cell, when you add your half reactions together, your E value always needs to be positive. Okay, and again, that's a spontaneous electrochemical cell. An electrolytic cell has a negative E value, okay? So it's going to be non-spontaneous. And this uses electrical energy or heat, right? So external energy to push a reaction against its potential, right? It doesn't want to go in this direction, but it does because of an external source. And I think Dr. Katie touched upon it. This would be like a rechargeable battery, right? Batteries like to use up their energy or use their potential to, I don't know, have your remote control to your TV work, right? It works because there's a release of energy from the battery, okay? So batteries are voltaic or galvanic. They are spontaneous, a normal battery. Rechargeable batteries, though, right, you plug into the wall, okay, to recharge. And so what's happening is an external source of energy, which is the electrical socket, is using its energy to push the battery, the rechargeable battery, against its potential, which means it's getting recharged using an external energy source, right? If you have a AA battery, it doesn't just sit there and recharge on its own, right? That would be against its potential. And so for a battery to recharge, it needs that external energy source, in this case, electricity. Okay. And so typically, if you also see battery, kind of meaning in the typical forward direction, that would be considered a voltaic cell. Rechargeable battery, when it's recharging, would be seen as an electrolytic cell. Um, and then just electrolysis is the process of pushing an unfavorable reaction forward, right? Electrolysis looks a lot like electrolytic. It's basically the process in which an electrolytic cell works. Just another term to know. Okay, and then just calculating our cell potential, which I'm sure you guys are very familiar with at this point. But they're both given in terms of reduction, right? They always show it in terms of reduction. And so one, you have to flip to represent the oxidation reaction. And when you do this, you change the sign on E. Okay? Some other terms that we can throw out here, right? A lot of times we see very negative values for E in terms of reduction, right? If it has a very negative E value, that means it probably likes to become the oxidation reaction, right? And why would that make sense? Well, when we flip it to oxidation, then it would have a very positive E value, which would help the cell become voltaic, galvanic, or spontaneous, right? Again, all three of those terms meaning the same thing. And so very negative E values in terms of reduction means they like to become the oxidation reaction, right? And remember that your reducing agent is what is oxidized, okay? So things with very negative E values in terms of reduction often are flipped, and they are often good reducing agents, okay? Just another term to know. And I know if you look in Dr. Katie's slides for this, it shows that in the slide that has all the different equations and all their E values, it actually shows that the more negative your E reduction is, the better the reducing agent it is. And the more positive it is, the better oxidizing agent it is. Okay, so that again could show up in terms of a theoretical question. So just be on the lookout for that. Okay, equations. So I actually use this slide for the equations because this shows two really important equations. And the ones I'm referring to is the ones that connect our cell potential E with K and delta G, right? So delta G naught is equal to negative N times F times our cell potential. So F is Faraday's constant. So again, it's constant. You'll be given that. N is the number of moles of electrons that are transferred in the balanced chemical equation, right? So in that first example we did today, that number would be 3. Okay. Now, when we relate K and E, E naught of the cell, so our cell potential, it is equal to RT over NF ln K. Okay, so just kind of recognize that it's E naught that is related to K or related to equilibrium here. Other things to note, our temperature will be measured in Kelvin, and our R value will be that 8.31 value, right? Do not use the ideal gas law R. That would be the wrong R to use. And the reason why is Faraday's constant, or F, is in terms of joules, and so our R value also needs to be in terms of the unit joules, which would be the 8.31 value. And again, N is there, and N represents, again, the number of moles of electrons transferred in the balanced chemical equation. The other really important equation you need to know is this equation. This is known as the Nernst equation, right? And what it does is it relates our cell potential to our standard cell potential, which is E naught. So again, if we go back a slide, when we look at the cell potential between standard E and K, our standard cell potential, or E naught, is in terms of our equilibrium constant. But when we solve for just our normal cell potential, or just E, it's actually in terms of Q. So what this tells us is that we use Nernst equation and we solve for E when we're not at equilibrium, right? We're at Q, it means we're not necessarily at equilibrium. In addition, it also tells us that our cell potential will change based on Q, which means it'll change based on the amount of reactants and products we have. And in addition, we always calculate our standard cell potential, or E naught, at 25 degrees Celsius, or 298 Kelvin. And so we use this equation, the Nernst equation, when we are at any temperature besides 25 degrees Celsius, right? If you're at any other temperature, you need to use this Nernst equation. Okay. Now, manipulations of E. As you'll notice, when you flip an equation, you change the sign on E. That makes sense. That's basically what we do when we go from a reduction equation to an oxidation equation. And that is the same thing that we do with thermochemical equations as well, right? It's the same as the manipulation of that for delta G. Skipping down, when we add equations, again, just like we do when we're solving for cell potential, we just add the E values together. Again, that is the exact same as thermochemistry. The really important thing that is different from thermochemistry that you definitely need to know, and it's a very common mistake, is that if you ever multiply an equation by a coefficient, there's actually no effect or change on our E value, right? And this is what the first problem we did today exemplified, that even if I multiply that potassium equation by 3, my E value stayed at about a positive 2.9, right? I don't also multiply that by 3. Okay, so definitely note that, maybe star it or highlight it in your notes. Okay, and lastly, just some units in electrochemistry. Again, coulombs kind of measures charge, so it measures the amount of electrons, with 1 mole of electrons being equal to 9.648 times 10 to the 4th coulombs, right? So that's a conversion unit that you'll pretty much use in any problem having to do with coulombs, or at least I'd say a lot, right? If we're looking at amperes or amps, units for that is A, and that is electrons per second, which we measure as coulombs per second, right? And again, that's what number 2 kind of dealt with. Now, volts, which is what we use to measure our cell potential, is actually joules per coulomb, right? So joules just means energy in general, and again, coulombs is a measure of amounts of electrons. Okay. Watts is power, so it's joules per second, and then joules is a volts times coulombs. So they could give you any of these and ask you to interconvert. Again, I think Dr. Katie has some good examples if you want to look through. It's at the very end of his chapter 18, lecture 2. So maybe look over those for a little bit more practice. I'm just not familiar with writing really good problems, I guess, for these types of questions. So sorry, I don't really have many. But definitely be familiar. I don't think it would be more than one or two questions. One question might be kind of using amps, volts, watts, joules, kind of interconverting between those. A more expected question, I think, would be converting to coulombs, which we kind of did an example of today. I just had you take it one step further to change it to ampere. Um, but yeah, if you're going to be familiar with one of them, I would say coulombs is probably the most likely to show up. But traditionally, it's not a huge focus. So be familiar. Definitely look over Dr. Katie's problems for a little bit more practice. But just know the units of them so you can interconvert. But I don't think it'll be the worst. Okay. So again, that's all I have for the review. Again, this isn't everything in all the chapters, but I do think it is pretty much all the big details. Again, the practice problems will be posted at 7 p.m. tonight. So definitely give those a look over. Mark any ones that you have questions on, and we'll be going over those on Wednesday. And yeah, again, they're what I think the exam will be pretty representative, but they obviously will have their own questions, their own ways of asking them. Topics I don't cover might be on their exam. Topics I do cover will definitely be on their exam. But yeah, and again, mark your questions, whether it's from this review or those problems, and I'll be happy to answer any questions on Wednesday. Again, that session will begin at 7 p.m. Okay, good luck studying, and have a good week.